Thank you for the introduction. So the problem was proposed by Kolmogorov. He asked whether it is possible to map sets in the plane with finite measure onto polygons with one Lipschitz maps in such a way that the image is a polygon. Here, a polygon is a set if its boundary can be covered by finite many lines. This problem is also related to the question of Lotkovich that Tamás mentioned earlier. If the answer is positive to this question for a set, then it is also positive for the question of Lotkovich. Unfortunately, this is not possible in general. It was shown by Balkayakis and Máté that there is a counterexample. In fact, there is an open and simply connected counterexample. However, if the set is restricted to be compact, then this is still open. So let K be a compact set. We call K measure Kolmogorov if the answer is positive for Kolmogorov's question. We will also consider a variant of the problem. We call K distance Kolmogorov if instead of small measure loss, we require that the function has small displacement everywhere. It was shown by Balkayakis and Máté that if every compact set is measure Kolmogorov, then they are also distance Kolmogorov. It's important that this does not necessarily hold for specific compact sets. For example, if K has Lebesgue measure 0, then it is vacuously measure Kolmogorov, but it is not clear if it is distance Kolmogorov. Actually, it is open whether it is necessarily distance Kolmogorov or not. I could show that the reverse implication also holds, but also for specific sets. So if K is distance Kolmogorov, then it is also measure Kolmogorov. For this, we use the following lemma, that if we have a one Lipschitz map on a board, and it has small displacement, then it also has small measure loss. But there's a problem. Recall that in the definition of distance Kolmogorov, F was defined only on the set K. But here we need it on the whole board. And we could extend it to a one Lipschitz map using Kirchhoff's theorem, but there's nothing guaranteeing that it will still have small displacements. But fortunately, we can do this extension in such a way that the displacement also stays small. The proof of this theorem is similar to that of Kirchhoff's theorem, but it is somewhat technical, so I won't go into the details. I'd also like to remark that, like Kirchhoff's theorem, this also holds for Hilbert spaces. Now, let's move on to the main question. Balkayakis and Máté asked whether the Sheltinsky carpet is distance Kolmogorov. They hope that if it was not distance Kolmogorov, then that could have shown that there's a counterexample also to the measure Kolmogorov problem. Since the Sheltinsky carpet has Lebesgue measure 0, it's equivalent to asking whether we can map it into the union of finitely many lines with small displacement. And it turns out that the answer to this question is yes, we can do this. And for this, we will use the cube null problem. We call a set in the plane cube null if it can be covered by strips of arbitrary small total width. It was shown by Carberry, Soria, and Vargas that such sets which are sigma finite with respect to the one-dimensional Hausdorff measure are tubular. Also, it was shown by Horongi that the Koch curve is also tubular. And finally, Pyörällä-Schmerkel, Suomala, and Liu show that the Scherpinski carpet is also tubular. Or more generally, they show that times n invariant fractals, which means that they are invariant under the map of scaling by n modulo 1, they are also tubular. My main result is the following. Assume that we have a bounded set with tubular boundary. Then it is both distance Kolmogorov and measure Kolmogorov. Note that these results are all in the plane. Later I will talk about the higher dimensional case. So the basic idea of the proof is to cover the boundary with finite many strips. We can do this by compactness. And then we want to map the strips into the union of finite enemy lines with the one-Lipschitz map. So basically, we want to push the regions towards each other in the complement of the union of the strips. We have to do this orthogonally, otherwise this map won't be one-Lipschitz. Here you can see an example of what I mean. We have two strips and four regions in the complement, and we want to push them together orthogonally. Unfortunately, this does not work. If we do this, then the images of the regions will overlap. And due to topological reasons, the images of the union of the strips must contain that red area, so it clearly cannot be covered by lines. And the solution is to cut off some parts of these regions so that after applying these translations, they fit together. So let's look at this example. Here, we want to cut off these green parts. And then we want to push the regions together. And then we hope that we can interpolate somehow on the union of the strips plus the green parts. So we want to investigate the union of the strips plus these cut-off parts. So basically, we want to combine the strips into some kind of generalized strip. So let's see the definition of a generalized strip. But first, we need the proximal map, which is used in convex analysis. If we have a convex function g, then the proximal map is a function from Rd to Rd. Here the R green denotes the unique minimizer, which is indeed unique by the convexity of G. The proximal map is always one Lipschitz, and also if G is L Lipschitz, then the displacement of prox G is at most L everywhere. And these are exactly what we need. Using the proximal map, you can define generalized strips. Assume that G is the maximum of finitely many affine functions. We could also call it a polyhedral function. And then we can associate a set SG to G, which we call the generalized strip. It consists of the points for which their image by prox is such that G is not differentiable there. This definition is not very intuitive. Let's see an example. Here you can see an example of a generalized strip. As you can see, it has these blue parts which are like strips, but there are also these green parts which are junctions between the strips. Now, if we apply prox G to this set, then by the definition, the image consists only of points where G is not differentiable. But since G is a polyhedral function, its non-differentiability points can be covered by finitely many lines. So basically what we want to do is to cover the Sierpinski carpet by a generalized strip. Then we apply prox G to the set, and then the image will be contained in the union of finitely many lines. What we have to be careful about is to make sure that the Lipschitz constant of G can be arbitrarily small. We define the generalized strip outer measure gamma as twice the total Lipschitz constants of functions for which their generalized strips cover the set. Now, if we have a closed strip, then we can write that closed strip as a generalized strip in such a way that the Lipschitz constant is exactly half the width. And from this, it follows that gamma of S is at most W. In fact, it is true that gamma of S is exactly W. So this is why we multiply by 2 in the definition. So for a strip, gamma gives us the width. The sketch of the proof is the following. We can write S in a specific form. Here, V is a normal vector of S such that its length is W over 2. And then if we write this function G, it is not that difficult to check that we indeed get back. A corollary of this proposition is that if a set is cube null, then gamma of A is 0, since for a strip, gamma is just the width. So now we know that gamma of the boundary is 0, but we still need to find some way to combine these generalized strips. And for that, we need the following level. Assume that we have 2 generalized strips. Then we can cover their union by a third generalized strip in such a way that the Lipschitz constant of the function h is at most the sum of the Lipschitz constants. It is important that in general, this S of h is strictly larger than the union. As you could see from the previous example, where we have to cut off some parts, S of h will contain also those cut off parts. I will sketch the proof of this. So we can write f as the maximum of f and g as the maximum of affine functions. Then we can actually write down h using an explicit formula. Here, nabla is the gradient of these functions, which is constant since these are affine functions. And like the previous proposition, it is not that difficult to check that this is indeed the correct choice of h. From this lemma, we can show that if we have a compact set, then gamma of k can be approximated by a single generalized strip. So this means that if we cover k by countable many generalized strips, then we can replace them by just a single generalized strip, such a way that the Lipschitz constant is still small. For the proof of this statement, there's a bit of a complication because generalized strips are closed, but we will need an open cover to use compactness. But this is actually not a problem. And from this statement, we have the following corollary, that if the boundary of the set is gamma null, then it is both distance Kolmogorov and measure. Since the boundary is compact, we can cover it using this previous statement, a single generalized strip of small Lipschitz constant. And then if we apply the proximal map to A, the boundary, the image of the boundary will be covered by finite many lines. And furthermore, we can also check that nothing bad happens inside A, so we will indeed get a polygon. Now some words about the higher dimensional case. Most of the proof works also in higher dimensions, but we need to use another property because tubnality is defined using the infimum of the total cross-section of tubular neighborhoods of lines. But for the proof, we need coverings by strips. By strip, I mean a set between two parallel hyperplanes. Fortunately, what Püerer, Schmerkin, Sommer, and Wu actually showed is that these times and invariant fractals are strip null. By strip null, I mean that it can be covered by strips of arbitrary small total width. So this means that the answer to Kolmogov's question is positive also for this class of higher dimensional fractals. But still, the strip null property is significantly stronger than the tube null property. For example, the sphere is not strip null because it is well known that if we take the intersection of a sphere and the strip, then the surface area is proportional to the width. But fortunately, by directly constructing a generalized strip, we can show that every regular C2 hypersurface is gamma null. And from this, it follows that if the boundary of a set of a bounded set in higher dimensions can be covered by countably many regular C2 hypersurfaces, then it is both distance Kolmogorov and measure Kolmogorov. Actually, instead of C2, we could also use the slightly weaker property that it is that as a graph of a function, it is the difference of two convex functions. And finally, some open questions. The main open question is whether every Lebesgue set is gamma null. It is true that if a set is gamma null, then it is also Lebesgue null. But the other implication is not clear if it holds. However, if this is true, then that gives a positive answer to Kolmogov's question for every Jordan measurable set. Unfortunately, this does not give anything about the Lotkovich question, but still, this will be quite an interesting result. My second question is whether the fractal calculation construction of Schmerkin and Sommer is gamma null. This is a construction of a set which is Lebesgue null, but not tube null. And also, the main point of the construction is to find a set which has any Hausdorff, which can have any Hausdorff dimension between d minus 1 and d. This is the only example of a set that is not tube null, but it is Lebesgue null. But I do not know whether it is gamma null. There is also another construction of a tube null set by Carberry-Soria, of a non-tube null set by Carberry-Soria and Vargas. But that specific example is gamma null, so that cannot be a counterexample. So if this was not gamma null, then that would be a counterexample to question number 1. Thank you for your attention.